quantum foundations and quantum gravity. He obtained his PhD in theoretical physics from Imperial College, and he is the editor of the journals Quantum and Cryptography. He's 2 times the general chair of the IACR International Conference on Public Key Cryptography. Petros, it's very good to have you, and the floor is all yours.
Hello, yeah. Thank you for inviting me here. I'm very happy to give a talk in this seminar series. Yes, so, well, first, let me correct, it's University of Edinburgh, not University of Nottingham, but I guess that was obvious from, from the affiliation here. Yes, so, yes, I'll talk about quantum algorithms for causal sets. So the talk is basically presentation of results of a project that I have, which is called Quantum Software for a Digital Universe, which is part of this EPSRC theme of quantum technologies for fundamental physics. It's a small grant in this scheme, and is also supported by the Quantum Computing and Simulation Hub by PhD students. So the idea of this project is to use quantum computing, and specifically quantum algorithms, for questions in fundamental physics, and the specific aim is target is causal sets. So here I'll present some early results, and it's kind of a general, talk of introducing the whole idea and these early results. Hopefully, maybe sometime later in this year or next year in the seminar series, there will be some more focused talk on one particular aspect of this. So it's going to be a bit high level, describing a number of things. And also, I'm not sure I could gauge correctly the background of people in this audience. So I made the assumption that people don't know about quantum computing and quantum algorithms. And I also made the assumption, perhaps less valid assumption, that people don't know too much about causal sets. So I kind of introduced things from the beginning. So apologies if it's boring some parts to people. Now, the people involved with this project, or the results I'll present, is a big list of people from Edinburgh, Imperial, and a few other places. Blue are the postdoc and PhD of myself and of Faye, that, kind of, I would say, did most of the actual work. Yes, so that's that. So now, the structure of this talk, I'll start with giving some introduction about what causal set is, very high level, and then about quantum computing. Obviously, both these will be pretty fast, but I start not assuming things. And then I'll also give some description about quantum algorithms and the distinction between what are known as fault-tolerant and near-term quantum algorithms, which is different. Then after that, I'm gonna touch on 3, questions on causal sets and what we can see about quantum algorithms for those: Benincasa-Dowker action, and quantum gravity partition function, and some recovery of geometrical properties from causal sets. So that's that. So now I'll start before introducing causal sets. I'm gonna say a few things about what's known as the quantum advantage quest, or whatever you've heard different terms like quantum computational supremacy, or other terms. So the idea is that one focus on one application. So I'll do like a break on this thing. It's funny because in this talk, when I say application is the task that you apply quantum algorithms. So usually one would think of fundamental physics as being the theory, and then the application being some engineering or technological use of this theory. Well, here, I mean, the picture is upside down, say, in a sense. I mean, so the application is the theoretical physics, and the topic that I'm doing is the quantum algorithm. So we apply the quantum algorithm to different things, and in this case is fundamental physics. So that's could be confusing. So one picks one application and identifies in this domain application, or if there are some things that require computational calculations, and specifically computational calculations that are expensive and cannot be efficiently done. I mean, there are blocking points for the the computational power is a blocking aspect, and then try to construct for those tasks quantum algorithms. Of course, it's not necessarily that the quantum algorithm would perform better, so one needs to consider the practical limitations and all the classical solutions. And then at the end of this discussion, answers the basic question that everyone has wondered: to quantum or not to quantum? Yeah, so does the quantum offer some advantage? And of course, if it does, it's interesting to evaluate when you expect to see this advantage. And yes, so here I'm not going to, even if we were to demonstrate that for this specific task in causal sets, you can find a quantum advantage using a quantum algorithm. That it would be, you would already know if this was the case with existing devices. So in a sense, I'm not speaking about already progressing the research in physics, but setting the agenda of phrasing the questions, the physics question that one is interested in terms of quantum algorithms. So when the devices become bigger, then you can accelerate the physics research using those type of algorithms. Okay, so now I'll move to a quick definition of causal sets. This is an approach to quantum gravity, causal sets. So I imagine that most of you have heard other talks on causal sets. So this is known to most of you, but I'm just giving the introduction. So the basic assumption to causal sets is that space-time is not the usual manifold, but is replaced by causal set, which mathematically is a discrete set that has the following properties. It's a partial order set, so between different elements you have a relation, and this relation is the causal relation, and it's also locally finite. So this means that if you take any two elements of your causal set and you count how many other elements are to the future of the one and the intersection of the future of the one with the past of the other, then there will be a finite number of elements there. So it's basically a discrete structure. So that's what a causal set is mathematically. Now, a lot of the algorithms that we're gonna see is basically, from the perspective of dealing with these things, you just need to understand this, that causal set is this structure that is supposed to replace space-time. So, if you haven't heard that, you would say, okay, so that's nice, a partially ordered set that is locally finite, fantastic. And why would they expect that this would look anything like a space-time, or that it could replace space-time? So there are some theorems, the one by Malamantine, quite old one, that basically says that the metric of a globally hyperbolic space-time can be reconstructed uniquely from its causal relationships up to a conformal factor. So if you are given, space-time manifold, and then you take the causal relations and then you forget the manifold completely and you just keep the causal relations, you can reconstruct the metric and the geometry you started up to some local volume factor. So in a sense, there's only one degree of freedom that is left to fix. Now, in causal sets, we have discreteness, and the assumption is that each element of this causal set corresponds to one Planck volume. So if you have an interval, this interval has a fixed number. You can count the number of elements in this interval, and then you multiply by Planck volume, and you have fixed the volume of that region. So in a sense, this discreteness brings you this number of elements, gives you this one degree of freedom that was missing in order to recover fully the geometry. So that's the high-level motivation why one would expect that the causal set can replace a continuous space-time. Okay, so fine, but why? Okay, so this is all nice, but why would we believe this thing? Why would we believe that there is discreteness? There are a number of indications for discreteness. Well, I just name a few. So there's finite entanglement entropy of a quantum field theory in presence of black hole. Holography is associated with finite data in finite area, and discrete area variables in spin forms, for example. There are other reasons why one would believe that there is nature is fundamentally discrete. And in any case, nature can either be fundamentally continuous or discrete. So it covers half of the cases. Right. So then the second element that is important for this talk is the concept of Lorentz invariance. So fine, we want we'll say, okay, let's take the view that space-time is discrete. But naively, if you just take a lattice, a discrete lattice, then that would not be Lorentz invariant. So here in this plot, you can see the red dots. The red crosses actually are not dots. So this is like a regular lattice, 1 plus 1 Minkowski. So you have just you just have a regular lattice. And now if you view the same points in the Lorentz boosted frame, then you'll get this green crosses. And even though your initial thing seemed like uniformly, so that you covered all the space, or its area, its volume in your, had this the number of elements you had was proportional to the volume area in this case. In the red case, in the boosted frame, this is clearly not the case, because here you have all this thing that has no elements. So we know that you cannot. Ordered lattices are not Lorentz invariant. But what you could have is you can have these random lattices, which is what causal sets are, which they're not are lattices that don't have this structure, and then these lattices preserve Lorentz invariance up to some small fluctuation, this random fluctuation. And there are some arguments and some recent paper by Faye and Jeremy that under some set of assumptions, one can show that the only Lorentz invariant discrete structure that is compatible with these assumptions is essentially causal sets. So now this is interesting for more reasons, because this means that whatever algorithms or whatever physics we do with causal sets, it doesn't need to be, you don't need to believe that causal sets is true or anything. You can use causal set as something emergent or as a discrete approximation. So if there are things that you cannot calculate in continuum, but you could in a discrete Lorentz invariant approximation of spacetime, then causal sets is your best way to do that in a sense. And also, even if there is some even more fundamental theory underlying nature that at some level, some scale, it emerges as discrete, but it also should respect Lorentz invariance. Then in that effective level, it would behave like a causal set. So in that case, also observing, analyzing properties of causal sets would be useful. Okay, so that sets the scene. So okay, fine. And then the next obvious question happens. Okay, so why would quantum computers be useful for these causal sets? So first observation is that those random graphs have very high valence, and this means that some analytical methods do not apply for some questions that involve graphs with high valence, and this means that you need numerics. Now, for most interesting tasks, the numerics scale very badly with a number of causal sets elements. Some case exponential, but even if it's not exponential, if it's fourth power or things like this, it's pretty bad. So tackling instances of numerically where interesting physics happens frequently is beyond our classical computational capability. So we can't even see the consequences of this assumption of discrete Lorentz invariant spacetime in a sense. So this brings the question, okay, can we do something better with quantum computing? Okay, we know that quantum computing in theory can offer computational advantages. So the question is, let's see what they can do. Do we have any specific reason to believe that quantum computers would be good for this type of questions? There is actually there are two further reasons. Well, even if there wasn't specific reasons to believe that quantum computing would give you impressive speed ups for those questions, it would still be worth examining the potential of quantum algorithms, since people are looking the potential of quantum algorithms for any random application that anyone have thought. So yeah, so that would make sense. But there are more reasons. So there are non-quantum computing algorithms that give speedups for graph problems, for example. But those graph problems usually are not directed, and they don't have high valence as the ones in causal sets. So in a sense, while there is promise that quantum algorithms could offer advantage for causal set questions, it's still a fruitful area to research, because those results have not been extended for the graphs, directed graphs that causal sets are essentially are. Also, another thing, in many cases, quantum algorithms, when they're applied to physics, one of the basic limitations that they have is that physics many times is continuous, and you need to, your quantum computer works with qubits, is discrete, so you need to kind of discretize your problem and make some approximations. And then this discretization and approximation usually is very costly in numbers of qubits and presents a limitation for the potential of quantum algorithms, especially in the near-term era. Now, in causal sets, a number of questions, at least your space-time itself is discrete. Of course, there are continuous things there as well, but quantities, but at least your space-time is discrete, and this saves you some of the extra cost that you would have in this approximation. So these are the two kind of reasons why one would believe that quantum algorithms would be particularly good for causal sets. Okay, so what quantum computers are. So now I'm moving in the second introductory part of this talk, which will be, I hope I don't, I really make the assumption that people don't know anything about quantum computers. So yeah, I hope it's not wasteful what I'm saying. So the idea of a quantum computer is to manipulate in a programmable and fully controllable and flexible way quantum information. And we are using, instead of bits, quantum bits. And because there are different properties, this defines a different computational model. So what is hard for a classical computer could be easy for a quantum computer. And here by hard and easy, usually we mean a hard is a problem that you don't have a polynomial time algorithm, and easy is one that you do have a polynomial time algorithm. But of course, there are other type of speedups beyond these things. Now, large-scale perfect quantum computers are not available yet, but there is a lot of progress, and quantum hardware has been developed based on different physical systems: superconducting, ion traps, photonic, neutral atom, silicon, and there's a huge different discussion speaking about the quantum computing hardware. But in this talk, I'm not going to speak anything about this other than the number of and quality of qubits that exist. Now, I would like to give, I could skip the next couple of slides, but I thought to give you this because it's an intuition that is not frequently presented. I believe that the reason, when you say why quantum computers gives a speed up, there are many ways, many justifications. You hear people saying, oh, it's entanglement, it's superposition, it's contextuality, it's whatever. And in a sense, it's all of them. But what I like to think is that quantum computers is like a probabilistic classical computer, which these are the BPP, bounded error probabilistic algorithms. But instead of probabilities, you have complex valued probabilities, you have amplitudes, basically. Now, what this means is that, so you have here a decision tree of an algorithm, let's say, that you can think this of like a coin, and you can reach, you can reach one outcome with different paths. You can go this way or this way. Now, classically, you have like probabilities are all, non-negative, and they add up. Now, quantum mechanically, of course, you can have cancellations here because of interference. Now, what this means is that when you have the full algorithm like this, there are a number of points that are not allowed, and then basically the branches of computations are kind of truncated because you have this destructive interference in a sense. So this is, and then when you have this probabilistic algorithm, usually at the end you make, you get one of the outcomes. But now there are a number of outcomes that have their probabilities amplified because some other outcomes were completely pruned. They were cut from early because of destructive interference. And that's kind of what gives you the speed up. It's not really that you do things in parallel. But in some sense, I mean, you don't do all the branches in parallel, because at the end you make a measurement and you take one of the possible outcomes. But at the same time, even if you take just a single path and the one that you at the end measure, somehow the particles know to avoid the paths that are ruled out by destructive interference. So you have some knowledge of what's happening in all configuration space, but you don't really do the computation in parallel. I mean, you have heard this thing. So basically, the speed up you get is because you have a clever algorithm. So it's not that you have faster operations. It's not that you run all computation in parallel, as I was just describing. This is one of the most common wrong cliche, that you're saying, okay, I can do all the, I can run a database in parallel and then I can find one element I'm searching. So this is not what actually happens, because and because of this, the advantage you get is not task independent. It's very specific on the problem and the algorithm you find. And actually, BQP, which is the complexity class of, the class of problems that you can solve in polynomial time using a quantum computer, is a well-defined complexity class, and it has some limitations. There are problems that are hard for this complexity class. For example, travel salesman that surely you've seen people claiming that you can, solve efficiently the traveling salesman problem using quantum computers. No, you cannot solve it efficiently. You might still be able to get some speed up compared to the classical algorithms, but that would not be an exponential speed up. Okay, so this was my quick introduction of how quantum computers work. Now, the size of quantum computers that exist currently, they have between 100 and 1,000 qubits, and those qubits are noisy. So you can get fidelity, pretty good fidelity. So you can get up to 99.9 fidelity. But if you have 1,000 qubits and you have 99.9 fidelity, this means that one qubit is wrong. If you want to make a number of gates or operations on this, then the chances of hitting, making a mistake increases a lot. So this is more than what you can classically simulate. If you have more than, in a classical computer, you can simulate up to a 50 qubits quantum computer, because the classical simulation usually scales exponential. So you would have 2 to the 50 classical bits for 50 qubits. And anything above 50, it's impossible even with the most powerful classical supercomputers. However, is less than what it's actually required to run generic quantum algorithms. Because to run generic quantum algorithms, you need quantum error correction. And quantum error correction means that you need to sacrifice 1,000 physical qubits to make just a single perfect qubit, in a sense. So you can actually see from the numbers here. So you can basically, with existing device, maybe we can have one perfect qubit. But having said that, there exists this concept of noisy intermediate scale quantum devices, NISQ devices, which are devices of the era we live now. And there are algorithms that are designed especially to be able to run in this type of devices. So I term these NISQ algorithms, and then there is the fault-tolerant era algorithms, which are supposed to run in this, like for larger devices. Okay, I see I am, not going very fast in my talk, but yeah. So I'm just going to list things for now. So quantum algorithms, they exist, the fault-tolerant era, as I mentioned, and the near-term era. People look at both type of algorithms. Known algorithms that give you exponential speed up, these fault-tolerant algorithms is factoring and some linear algebra tasks, this HHL algorithm. And also simulating quantum systems, which is one interesting, especially for this community, category. And then you have smaller quadratic or polynomial speed up for other problems like unstructured search or optimization, such as the traveling salesman problem that I mentioned earlier. Now, I'm going to say a few more things about Grover, because we used Grover algorithm, and it's kind of nice. So Grover is the example of this unstructured search algorithm. So the idea of this algorithm is that you have a big database that is not structured, is not alphabetical, let's say, and you want to find one name in this database. And classically, the best you can do is just randomly start searching all the book to try to find the name that you are looking for, and requires to search at least order n, where you have a database with n elements, you need to search order n times. Now, it's known that you can do quadratically faster with quantum computers, and this is kind of the algorithm. I think I'm running a long time. I wanted to explain how this algorithm works, because it has a very nice geometrical picture, but I don't think I'll do that this time. But the idea is basically that you start with equal superposition, and then you can generate the quantum state that has in the quantum state itself, it has a pointer, which is the thing that you want to find, in a sense. So you can do this with one step. But if you do this, then you cannot extract this information, because to extract this information, you need to make a measurement. And when you make so you don't have access in the amplitudes itself. You need to make a measurement. And when you make a measurement, the probability of just hitting the correct element is exactly as it was classically. So instead, so you cannot actually just do the superposition and measure. You need to do a number of tricks. And every time you do this subroutine, you can amplify the amplitude by a constant factor. But you amplify the amplitude by 1 over square root n. So you just need square root n steps to make the amplitude as order 1, and then find with probability 1 the solution. Anyway, so this was it. On the other side, so there are these fault-tolerant algorithms. On the other side, there exist these near-term algorithms. And the majority of those algorithms have a starting point, a single problem known as the k-local Hamiltonian problem. So the k-local Hamiltonian problem, you're given a Hamiltonian that has a polynomial number of, it's a sum of different terms. And the number of terms is polynomial in the size of your problem that you're considering, and each of those terms acts in at most k qubits. And you can actually even do a 2 local Hamiltonian, so you can have this, that each of the terms in your sum acts on 2 qubits, things like this. So you have this Hamiltonian, and the question is to find the smallest energy, the ground state energy of this Hamiltonian, or else the smallest eigenvalue of this matrix, essentially. And this sounds like a very, okay, fine, good, you can do that, but why would I care? We would care because this problem, it can be shown that is QMA complete. And this basically means that any interesting problem that the quantum computer can solve efficiently can be bumped in this type of problem. And actually, not only this, many problems that quantum computers cannot solve efficiently, they can also be cast in this form. So it's actually a really, really wide class of problems. Of course, if you really want to solve, to use this approach, you need, and you have a given problem, you need first to map your problem to the ground state of Hamiltonian, and that's not trivial generally, as we'll see later. This is kind of the tricky thing. Now, there exists a class of algorithms, variational quantum algorithms, quantum annealing, adiabatic quantum computing, that all of them are based on this Hamiltonian, on the k-local Hamiltonian problem. The ones I focus more is this variational quantums, which are hybrid algorithms that they have a classical part and a quantum part. The idea is that you use the quantum part to do the expensive thing. However, the quantum part is just short depth, because if you have a circuit that has long depth, because you don't have perfect qubits, the more depth you have, the higher the probability that you have errors. So what you really want is you want your quantum part to be simple. Just you prepare, you do a short circuit and then you measure, and that's it. You don't store the results, you just store the classical information. So the idea is that you have this, you initialize your state in standard quantum state, then you run a quantum circuit that is parameterized with these angles. You make a measurement, you take these outcomes, you repeat this a number of times. You take these values and you estimate the energy of your Hamiltonian on the state psi theta, which is prepared here. And then you just do a completely classical optimization process to find the minimum of, the values of thetas that minimize this quantity. And then this is your best guess for the ground state of the Hamiltonian you try to solve. So the quantum part is very simple. Again, it's just start state, the same type of circuit, measure, take some classical values, then you do the classical optimization, and you go on. And this type of approach, these are also known as parameterized quantum circuits, and they are used for variation quantum eigensolver, quantum approximate optimizing algorithm, and quantum machine learning. All those use the same meaning. Okay, so enough of the introduction. Yeah, so more than I don't know, 2/3 of my talk went to introduction, so that's great. Yes, so I'll go with the first question. So quantum algorithms for causal sets, the BD action. So basis for path integral approaches to quantum gravity is, I think that is one thing that definitely is well known in this audience, is the Einstein-Hilbert action. So what we would like is an analog to for causal sets, an analog that is defined with respect to the causal relations. So that if I have a causal set and no information about, you know, the corresponding space-time or whatever, I can define this action. And this action exists, I mean, different more refined versions, taking into account boundary terms, etc., and different dimensions were developed later. But the first one was this paper with Benincasa-Dowker back in 2010. And it's given with respect to this expression. So basically, well, here is the 4-dimensional scalar curvature. So and then obviously the action you can just sum over the scalar curvature over all the elements of your causal set. Now this, as you see, this has a number of different terms, n0, n1, n2, and 3, and each of those nk is defined solely with a causal relation. So this given an element x, and 1x is all the elements that the volume between your starting element and that element is 1, and 2 is all the elements is the number of elements that have this relation. So basically, you basically want to count all the 2 chains between your x and any other element. You count all the 2 chains that exist, and this gives you this n1 quantity, n2, and so on. Now, these quantities can be directly computed by counting occurrences of small subgraphs, and you can do this from the adjacency matrix. So all this was known, but of course, to do this calculation is very expensive, classically. And here I'll give some results we have. So basically, now I mentioned here time and space complexity. So what space complexity means is how many qubits, well, or how many, you know, what space you need, what memory you need in order to run the algorithm. And time complexity means, you know, like how many steps in time you need your algorithm to run, how long you need your algorithm to run. And if you have the naive classical algorithms runs as n cube, now n is the number of causal sets elements, and you can understand that if we are talking about, you know, a discrete spacetime, you want n to be large. So n cube becomes, you know, really prohibited. And any improvement on the time complexity of this would be great. You can have those classical algorithms that do better than n cube, but they are really not practical. So they're known as galactic algorithms, in the sense that the complexity goes n to the 2.38, but the constants in front are huge, and practically, actually, people don't use this algorithm at all. So this is the thing that people practically would use. Now we had a quantum counting algorithm that is based on Grover, that we can reduce the time complexity to quadratic. The space complexity needs to be linear, but I mean, we had an idea. We haven't proved whether we can do it to reduce it even further to logarithmic in the number of causal set elements. But this would be really important for actually running this algorithm, because the number of qubits you have, I mean, the space complexity for classical algorithms is irrelevant, because you can, I mean, you can have you can parallelize you can use high performance computers and so on, but for quantum computers that is relevant. So I mean, reducing this to this would be important. And also we tried to use the HHL algorithm, which in some cases HHL gives exponential speed up. So we thought, okay, let's try maybe it gives something better, but there were a number of reasons why this fails, and basically you can't get better than this. Actually, you get worse than the classical case. So that's the idea. But because our algorithm, our quantum counting algorithm for the BD action is Grover based, so use the Grover algorithm, this means that it's fault tolerant. And fault tolerant means that you need quantum error correction, so it's not really promising for at least for the next, I don't know, 5 years in the super optimistic, view, or more realistically, I don't know, 10, 15 years. Of course, I guess research in quantum gravity doesn't move that fast, so we could, in theory, wait for them. But yeah, I would try to do something better than that. Okay, so then the question is, how can we address the same question and using near-term algorithms? Yes, you can map Grover's algorithm to adiabatic quantum computing. So essentially, you can have a version of Grover's algorithm that you map it to a k-local Hamiltonian problem, essentially. And of course, adiabatic quantum computing itself is also not near term. But we recently had a paper that makes a near-term version of adiabatic quantum computing that you can actually run Grover, and we did that. So we can calculate the BD action using this NISQ quantum algorithm. However, it's not. I mean, we haven't done. The NISQ version of this algorithm doesn't have the same guarantees about the time complexity, about the performance of the algorithms. So we need to recover this to see whether it's still promising approach to take. The other way was to just directly try to write the BD action in terms of some constrained Hamiltonian. So this is a horrible expression, and given the time, I don't think I'm going to describe. But the point is that I had a student that tried to say, okay, let's make Hamiltonian formulation of the maximal disjoint isomorphic subgraph selection problem. So basically, we said that BD action reduces to counting subgraphs, and we say, okay, so let's do that. And you can get this, but unfortunately, this Hamiltonian corresponds when your subgraph are disjoint, and this is not the things that we want to count for causal sets. We want the, without this word, the version of that Hamiltonian that we haven't done yet. So that's ongoing. And might be harder, actually. Well, it will be harder. That's the reason we first did the disjoint one. So that's the first application of quantum algorithms to causal sets. The second one is what's known as quantum gravity partition function. So the path integral for quantum gravity requires the calculation of this partition function. So basically, this is a Euclidean version of the action. And then one needs to examine observables. One can use this partition function. But the question, and the question that we try to answer is, so how to sample causal sets according to probability distribution defined by this partition function. Well, here I'm just first reporting the existing prior classical results. So Sumati Surya and Will Cunningham, they had 2 papers on using Markov chain Monte Carlo for doing that. So the idea of Markov chain Monte Carlo is that one starts with a configuration, which in our case is a causal set. You construct a new configuration, C prime, and the way that you construct this is according to some mechanism. It's a local move or whatever, but it follows some probability distribution here. And then you have an acceptance criteria. So you see, so if the new you get a new configuration, and instead of calculating the probability of each, you calculate the ratio of the probabilities, which is much simpler to do. And if the ratio of the probabilities is smaller than 1, it means that the new configuration is more probable, and you keep that. If not, then you still may keep the new configuration, but according to this rule. And the idea of this Markov chain Monte Carlo is that you get new and new configurations, and after a long time, this thermalizes. After many terms, it thermalizes, and you end up with the correct probability distribution, basically sampling from that probability distribution. The problem is that many steps. So this is known as thermalization time. So how long you need to run this Markov chain Monte Carlo to thermalize. And in general, for interesting questions in causal sets in 3 dimensions, let's say, I mean, it didn't thermalize. So the question is, can we do better? And the answer from the quantum side is yes, we can do better. There exists something called quantum enhanced Markov chain Monte Carlo, which was a paper from last year by Leiden et al. And then the idea is basically that it follows the normal Markov chain Monte Carlo. It just gives you a different way to do this step. So how to sample the new configuration. So instead of having some local rule, okay, I have one causal set and I change this relation. Instead of doing that, you evolve the system according to a Hamiltonian. I'm not going to exactly say what this Hamiltonian is. The point is that this Hamiltonian also depends on the BD action, so Benincasa-Dowker action. And then you evolve this, and then you measure it, and then you just and this gives you a sample, a new causal set, and this is your new guess. And this has the advantage that in a sense, you're not obstructed. You can get things that are far configurations that don't look to the starting configuration, yet they are close in energy in a sense. So they're good. They have a number of good characteristics. And what they proved in that paper is that you can have quadratic to cubic speed up in the thermalization time, at least what they could do. So this algorithm was not done for causal sets. I mean, I need to specify this was done for different like Ising Hamiltonians. But the limitation of this approach is that actually you need qubits as many as the qubits of your problem Hamiltonian, which in our case is basically this action, the Benincasa-Dowker action, and that would correspond to quadratic. I mean, if you have a causal set with n elements, you require n square qubits to do this algorithm. So that wasn't great. So what we did is we recently had this result with my student Stuart, that you basically essentially are able to, I mean, I really run out of time, so I'm just going to say the result. So the result is basically we can retain the same speed up that they had in that paper, but basically we can use just a linear number of qubits. That was interesting result. But again, both these results were done in different problems in Ising models. So the idea was, I mean, the problem was that if we did it in causal sets, I mean, and I mean, we can simulate up to 50 qubits at most, and actually practically maybe something like 30 qubits. So if we want 30 to be the square of the causal set elements, this means that we're talking about a causal set with 5 elements. So that wouldn't be very interesting to start with. And of course, that's why we first checked this type of thing. But yeah, it remains to apply this idea to causal set, especially now that we got this quadratic speed up, it might start being interesting. Okay, the final set of questions is how to recover the geometry. So one thing that one can think of is the time-like distance between events. So you have the time-like distance between events in the causal sets. You can compute this by computing the longest chain between those two elements. And what we did is, okay, we obtain a Hamiltonian that the ground state of that Hamiltonian gave you the longest chain. But actually turned out that solving this problem is worse than the classical solution. So this is one of the cases that our answer to the question to quantum or not to quantum is not to quantum in this case. Other thing that we've considered is, so there are a number of, to quantify a causal set. A causal set in general could or could not resemble with a manifold or could have, so there are ways to estimate some quantities of causal set using machine learning. But one of the problems to use quantum machine learning is that you cannot load, large classical data sets in an ISC in a quantum computer, basically. So what we have developed, or COVID developed, is the idea that started by a paper of Haro that uses the concept of core sets. So core set is if you have a given data set with, like a big data set, you can define this core set that with respect to the quality of the thing that you're looking, so it could be the dimension of your causal set or something like this, you recover a smaller data set of weighted elements, weighted datums, data points anyway, and that the difference in the thing that you are computing in your initial set with a smaller set is bounded by epsilon. So there exists this technique, and of course, if one does this to reduce the size of the causal sets to a weighted set with fewer elements, then you can calculate this quantity of interest for the smallest causal set. Again, we haven't applied this to causal sets yet, so we developed this method in the general setting. So this is hopefully, I don't know, in the next time that one person from our network gives a talk here, we'll be able to report in progress on this. So I think I'll finish up with some future works. So interacting field theory on fixed causal sets. This could also give indications of phenomenological implications of this fundamental discreteness that could be detected. So there was recently Emma, Stav, and Fay had this paper accepted in Physical Review D, which is the classical analysis of this problem, and we are looking on how to help get forward this with quantum algorithms. Then black hole entropy. There is this idea of counting causal set molecules, and then we could again, there are counting algorithms for counting quantum algorithms that give speed up. So that would be one place to look. And finally, quantum dynamics of causal sets, like in the sense of quantum simulation of growth process. This is more in line of what, like, we would simulate the growth of the causal set itself, and so it's more like in the spirit of the quantum sim FP, what you call the network. Now, of course, in all these cases, one needs to look at the implementation in real device and the effect of noise to actually see whether these theoretical advantages that we described persist. And if it does persist, then one can actually run it in devices. We are gradually getting access on devices with hundreds of qubits, so it might start being a real possibility in the next couple of years to actually run any of those promising algorithms in real devices. And then once we have done this analysis, then we should determine the final answer, whether we should use quantum computers for this task or not. So it's kind of, we want to really answer the main question of this talk, which is to quantum or not to quantum. That is the question. Whether it is nobler for the problems to suffer outrageous computation times or to find the path against a sea of noise and by quantum advantage solve them. So thanks, I'll stop here.
Thank you very much, Petros. So are there any questions in the room? Feel free to post questions on chat or just unmute yourself if you would like to ask Petros any questions directly. So this is very much a little bit outside of my wheelhouse as an experimentalist, so I'll ask what might be a very naive question, but do you think that when you eventually get to the stage where you're going to be able to implement these sort of algorithms on an actual device, do you think that potentially just taking that implementation route, there's anything kind of fundamentally new that you can learn going that way, or is it just really a test of whether or not the kind of time constraints for these algorithms is going to be viable?
Yeah, so I mean, so the approach of our program is essentially what is known as digital quantum algorithm. So it's, in a sense, you're not going to learn any new physics from the algorithm itself, I believe. So you may learn things about the complexity of those algorithms, how they're affected by noise, but that you can also do in theoretical level. So there exists, for example, results that tell you that if noise is, in this problem, noise is above that level, then you can have a classical version that would beat the performance of this computer. So you can do this type of analysis, but I don't think that any of those would give you fundamentally new insight in the especially the fault tolerant algorithm, definitely not, because you just use a different computational model to solve it, and it's just a regular algorithm. So you don't simulate physics itself. Apart perhaps from this last direction that I mentioned about simulating the causal set itself. But again, I mean, it's not simulating the causal set. I mean, it's in a digital simulation, less than analog simulation. That would be, would perhaps give you insights on physics.
Okay, thank you. Any other questions?
I have a question. Maybe I wanted to have a chat with Petros afterwards if he wants to stick around a little bit.
Happy to stick around, yeah.
But we can take this offline. Yeah.
Okay, well, thank you very much, everyone. The next seminar will be on the 4th of June and will be at 3:30 UK time. We hope to see you all then.